Welcome all. This is a very good problem in which you can visualize that how physics makes a mathematics problem very easy. So the question says that there is a sphere which is rolling on a horizontal surface without any slipping at the contact. You have to find the radius of curvature of the trajectory of point A when it is at r/2 distance vertically above the center of the sphere. That means you have to find the radius of curvature of the trajectory of A. A will be moving something like this. So if you try to attempt this question mathematically, it is going to be very complex. But if you apply the physics laws in this, see how easy this question becomes. Suppose this is our ball at some point, and you see if O is the center of this point, let us call this O, and the A which is at r/2 distance, it is over here. Okay, now as the ball rolls on the ground, A will be, this is point A will be moving something like this, isn't it? As in the ground frame, this is the trajectory of A. This OA is what? This is r/2, where r is the radius of the ball. So this is the trajectory of A. At some instant of time, let us say the ball has reached over here, and this is the vertical diameter of the ball. So the center O is here and A is vertically above O. Okay. Now you see what is the velocity of the center? It is V. And we know it is pure rolling and a non-accelerated rolling. That means what is the angular velocity of the ball? Let us say omega. Then we know for pure rolling V is r omega. Okay. Now you can see that the center is moving with uniform velocity. That means it can be used as an inertial frame of reference. So let us observe the motion from the center of the ball, and in the frame of center of ball it will be a pure rotation. Let us say like this. In the frame of center O, and A is here, O is here, and if we are observing in the frame of reference of center, then it is a pure spinning ball, we can say. Now what is the acceleration of A with respect to O? Acceleration will be in radially inward direction, and it will be centripetal acceleration. That means what we can write? Acceleration of A with respect to O is centripetal what? Omega square r/2. Okay. And what is the acceleration of O? You see O is moving with uniform velocity. That means acceleration of O is 0. And if you apply the relative acceleration formula, AO is what? AA minus AO. And if you put it over here, that means what you get? We get acceleration of point A is AAO only, and which is omega square r/2. Okay. This we got from pure spinning motion consideration of the ball. Now come back to the ground frame, and you see at this point what is the velocity of A? If it is doing pure rolling, we know that if the center is moving with V, this will, and this distance is r/2, OA is r/2, then using V equal to r omega, this velocity will be what? This will be nothing but 3V/2, isn't it? Because this whole ball is instantaneously at this instant rolling, and it is, we can consider it rotating about this point. So if this velocity is V, then using V equal to r omega, 3V/2 is the velocity of A at this instant. Now this is the velocity, and let us say the equivalent radius of the trajectory at this point is r equivalent. R equivalent is the radius of trajectory at this point, and this we have to find. So if R equivalent is the radius, let us draw an equivalent circle like this, and the center of this equivalent circle is somewhere here. That means R equivalent is this. Okay. So in ground frame, you can assume point A to be moving on this circle at this instant of time. So what is the acceleration of A if you observe from this center? It is nothing but acceleration of A is what? In ground frame it is, I mean in respect to O dash it is V square upon R, again the centripetal acceleration only. Centripetal acceleration, that means what? Velocity is what? 3V by 2. So 3V by 2 square upon what? R equivalent, isn't it? This is A we got from the instantaneous radius of curvature, and this should be equal to this one because you got over here. So just equate and you'll get the answer. How? Write it. Omega square R by 2 is 1 upon R equivalent times V is equal to R omega. So put it over here and you get what? 3 by 2 R omega square. If you cancel and solve all the things, you get R equivalent is 9 by 2R. And this is the answer. You see how easily you got the R equivalent. And if you could have dived in the mathematics, then you should have find the equation of this trajectory yx. Then there is a formula for the radius R equal to d square y, something like this. The big formula is there. You would have put and then you have got the answer. But by physics, you easily got this equation. Okay. So similarly, let us watch the next problem. This is another good question. Here, there is no friction anywhere. This rod is constrained to move in the vertical direction. This ball, I mean this hemispherical surface is bound with a string over here. And the question is saying, if the string is just cut, you have to find the instantaneous acceleration of the hemisphere, the instantaneous acceleration of the rod, and the normal reaction force at this point. Okay, so let us approach this question. Suppose this is the question. Now, one part of the question is saying you have to find the tension T when the system is at rest and string is still intact. So, very easy question. Let us say in this instant, the normal reaction is N. So, the hemisphere is applying N force on the rod end and the rod is applying N force on the hemisphere. So, just apply the forces and everything is at rest. So, you get the answer. What? N is acting over here and this angle is theta given. So, N is over here and rod mass is small m and the hemisphere mass is capital M. So, this is something like this. So, N is m, I mean here, and you write it, this is theta. So, from here you get what? N sin theta is equal to mg. N sin theta is equal to mg. And if you watch the motion horizontal equilibrium of this hemisphere, then what is it? The hemisphere, if you see, I mean this is the N force acting over here and this angle is theta. So, what is the horizontal? And this angle is theta. So, N cos theta is acting because of the rod and because of the string, tension T is acting. That means this N cos theta should be equal to T and you write it. So, you get what? N cos theta is T. That means if you have to find T, then very easily you can say what? Tan theta is equal to mg upon T. And so, T is equal to what? Mg cot theta. This is the tension in the string when everything is at equilibrium and rest. So, very easy this part. Now, next part. In next part, what is happening? That string is just cut. So, let us move to the next part. String is now just cut. Then what is happening? As the string is cut, this rod, I mean already this rod was pushing the hemisphere. So, as the string is cut, this hemisphere will shift, I mean start moving towards right with some acceleration. Let us say how much acceleration? AH. Okay. So, in a very small interval of time just after the cut, this hemisphere will be shifted by, let us say, dx. So, I am shifting it, watch it carefully. This is the shifting. Okay. That means this in distance is how much? this shifting is, let us call dx. Now, if the sphere has shifted by dx, then this rod would have moved down by how much? It will have moved down by dy, let us say. Now, you see very small triangle, this one, this one, this one. I mean, let me use the red pen so that you can understand it better. So, watch this triangle, this, and this. You see, if this angle is theta, so angle between, I mean, this angle is 90 degree, so this angle will also be theta. Let me draw it bigger so that you can understand it. You see, the same triangle, I am drawing it in a bigger space. So this is the situation. This angle is theta, this is dx, and this is dy. So what you get tan theta is what? Tan theta is dx upon dy. So you can write it, dx is what? Tan theta dy. Tan theta dy. If you differentiate with respect to time and do it twice, then you get the relation between the AH, let us say the initial acceleration just after the string being cut of the rod is AB downwards. So you got a relation between AH and AB. What is it? This is AH, this is AH. So AH is AB d square y by dt square is vertical acceleration of the rod, AB tan theta. Let us mark this equation as 1. Okay, first equation. Now we will consider the forces normal reaction just after the cut. I mean, just so suppose just after the cut, this is the situation, and let us say the normal reaction between them is N over here, and on the rod N over here. Note that this N will not be the same as when it be found when string was not cut. This N will be different, okay, because now acceleration is there. Previously there was no acceleration. So let us now apply the equations of forces. On the rod, if you apply, you get what? This is rod, N is over here, and this angle is what? Theta. As you have seen, this angle is theta, and here it is what? This is mg. So, and we know it is moving downward with acceleration av. So just write for the vertical, it is constrained to move in vertical, so no need to consider the horizontal. So you write it, what you get? Mg minus n sin theta is what? MAV. MAV. This is second equation. Now watch the hemisphere. On hemisphere, what is happening? N is the force acting radially inward. So the horizontal component will be what? This angle is theta. So horizontal component is what? N cos theta. N cos theta. And this is the only force which is trying to push it with acceleration AH. So we can write N cos theta is capital M, which is the mass of the hemisphere, AH. So you see, you have 3 equations and 3 unknown, AH, AV and N, and these three are required in the question. So you can very easily solve these 3 questions, and on solving you will get what? You will get AV is mg upon m plus small m plus capital M times tan square theta. AH you get what? Mg tan theta upon m plus m tan square theta. And the normal reaction between them just after the cut is capital M small m g sin theta upon m cos square theta small m cos square theta plus m sin square theta, m sin square theta. So this is the answer. You might need to slightly rearrange them so as to match with your solution. Okay, so let us now watch the third problem. Third problem is, here is a spring block assembly, and note here it is the frictional surface, it is not smooth, and the question is that, and the spring is compressed initially by D. Initially the spring is compressed by D. So the question is, what should be the value, or for how many values of D the system is going to lose its entire mechanical energy. Do you know the meaning of losing entire mechanical energy? The meaning of this is that when the block comes to rest, then extension in this string is 0. That means the block should come to rest only at the mean position. Mean position means extension or compression in the string should be 0. Okay, so with this in mind, let us approach this question. Suppose initially the block is lying compressed. Okay, it is compressed by how this dash line represents the mean position of the block when there is no compression, no extension. So this distance is D. Okay, now from here, if you release the system, this block will come at some point, it will reach over mean position, and here let us say its velocity is capital V. So with this velocity it crosses and it reaches up to some point over here. That means here the spring is extended by how much? Let us say D1. So here it was compression D, here it is the extension D1. Now you apply the energy conservation in this part. What is happening? You see, initial energy is what? It is half kd square. Now minus mu mg, work done against the friction, that is minus mu mg d. This is the kinetic energy over here, because here this is the mean position, so there is no potential energy, so we can write it half mv square. Okay, now here from mean position to other extreme position at D1, let us apply again the energy conservation. Energy conservation doesn't mean, many people think that energy conservation is not applied when friction is there. It can be applied, just you need to consider the heat lost in the friction. So let us do over here again the same. What is happening? Initially at this point, what was the kinetic energy? Half mv square, half mv square minus mu mg. Now it will be d1, because distance moved after the equilibrium is d1. Should be what? Energy over here. Here there is no kinetic energy, only potential energy in the spring. So it is half k d1 square. Now what you do, you simply add these two equations. So you see here this mv square and half mv square, and this will cancel, and if you bring this k d1 square in the LHS and both these two in the RHS, you get what? Half k d square minus d1 square is mu mg d plus d1. Okay, so if you reorganize it, you get what? D minus d1 is nothing but 2 mu mg upon k. Okay, now you see the whole story can be repeated again. Now from, if the block starts moving from d1, then it again crosses the middle position with some velocity and reaches finally to this position where the spring compression is how much? Let us say d2, and the process will be repeated. Here again spring will be extended by how much? Let us say d3. So this to and fro motion, you see this to and fro motion, here, it will go on, and finally the block has to come to rest at where? At the middle position, as per the condition of the question. So if you go on writing, you see d minus d1 here, you apply the same over here, then you will get what? You get d1 minus d2 will again be the same. You can try applying the same condition, again you will get the same 2 mu mg upon k. Similarly, d2 minus d3 will be what? d2 minus d3 will again be the same 2 mu mg upon k. So actually this will go as an infinite series. And now if you see under what conditions the block will stop at the mean position, let us now analyze those conditions. So first condition is what? That when the block begins its journey from here, it doesn't cross the mean position and comes to rest only in this distance, isn't it? It doesn't go this side at all. In this situation, what is happening? d1 is 0. d1, this distance, I mean the block is not crossing the mean position and stopping there itself. That means d1 is 0. So if d1 is 0, you see what is the value of d? d is 2 mu mg upon k. 2 mu mg upon k when d1 becomes 0. I mean the block is not crossing the mean position even once. Now second condition, what? The block starts here, crosses the mean position, goes to the other extreme, and while returning back, now it stops over here. That means it is stopping over here, it is not going over here. That means d2 is becoming 0 in second condition. So if you put d2 equal to 0 over here, you see d1 is 2 mu mg upon k, and if you put this 2 mu mg upon k over here, then d becomes what? 4 mu mg upon k. d is what? 4 mu mg upon k when d2 is 0. So you see similarly, if you again try this, then you get d is what? 6 mu mg upon k. d is equal to 8 mu mg upon k. So actually you see for all these, here d3 is 0, here d4 is 0. So for all these values of initial compression, the block will come to rest at mean position only. That means there can be many different values of d, and you see the values of d are in AP. D are in AP. So you can identify which options are correct. So I hope you got the concept, and if still there is anything, any doubt is there, please feel free to ask in the comments. Thank you.